Well, the dandelion fruit comes from the dandelion flower. Most seeds travel about 2 meters from their parent plant, but there have been reports of these parachuting fruit getting carried over 100 meters, and there are even reports of them getting carried over vast swathes of seas to like 150 kilometers. So it's unpowered flight getting incredible distances. Each dandelion fruit is made up of a seed connected to a feathery drag-enhancing parachute, which she calls a pappus. If you look down on top of the parachute from above, it's 90% empty space. Between filaments, there's a thick boundary layer, and it effectively prevents air from penetrating through the parachute. And so it turns the fluid around the parachute, and it disgenerates this vortex of flow above the dandelion, which kind of just sits above it like a little halo. And this low pressure zone enhances the drag coefficient of the dandelion. The amount of drag that it can generate per unit area of material is quadruple that of what a disc would be. And when I say a disc, I mean that's how we design parachutes. We design impermeable surfaces. If you gave evolution like material and says, okay, build me a parachute, and it built a disc, not only would it fall twice as fast as the dandelion, which is a bad thing because it's going to stay up in the air for as long as possible, but also the wake that it would generate with that material is it would be unstable. Whereas the dandelion, not only does it get more drag, it also stabilizes the wake. So it's kind of like it's reached a kind of sweet spot in the design space. Parachutes have been around for quite a while now, and people are pretty good at designing parachutes for human fly. It's just when you then take those principles and then try to miniaturize them down, they don't quite apply. Because things are being miniaturized all the time, and especially flight, if you said, okay, make me a parachute, and you got some sort of fabric and used that, you wouldn't have an optimum solution. Evolution has done all the hard work for us. So, why not just use that?
I investigate turbulent flows with the aim of controlling their behavior. In my particular case, the process goes through numerical simulation. We use massive, larger simulation of direct numerical simulation of turbulent flow, but those are very expensive procedures, those full simulation, because they might take even months or even years sometimes. We are looking also at flow over canopies. Flow over canopies are very important for geophysical flows because people want to understand how vegetation intake oxygen and nutrient. Imagine a set of toothpicks clamped on a wall. Above those toothpicks, there is a complex flow. We are discovering that the transport of scalars towards the canopy and out of the canopy is governed by some very large vortices, which are living on the top of the canopy and on the edge of the canopy. This makes us believe that probably you can design a canopy. For example, say that you have a canal or you have a river, you can actually design the type of vegetation and how to seed the vegetation to obtain certain effects.
Because of the low density in the Martian atmosphere, the Reynolds number associated with flying on Mars is much lower than on Earth, and that changes the physics completely.
If the density is 1/100th that of Earth's, we get a lift force that's 1/100th than what you need.
But it seems that the Mars atmosphere is uniquely suited for bio-inspired flapping wing motions. We took a bumblebee which flaps at 150 hertz. One of the nice things about insect flight is that they can hover but also move forward and perform agile maneuvers. So it's not that we can simply take insect motion and play that on Mars. We have to be really smart about how we dynamically scale morphology and also wing kinematics.
We work in a computational group, and we model the lifting forces on the wings, and this is coupled to a flight dynamics solver, which models the wing and body interaction and the reduced gravity. And eventually, we also want to experimentally validate this in our vacuum chamber. It's definitely possible, and we would like to get this done as soon as possible to maybe aid in the human exploration of Mars.